Okay, let's go ahead and continue on with number 5. It says which of the following is true for sulfur dioxide and it should say it's electron geometry, molecular geometry, and OSO bond angles. In other words, we're looking for the electron geometry, the molecular geometry, and its OSO bond angles. So let's go ahead and start by drawing sulfur dioxide. Sulfur dioxide would be SO2. It's a neutral compound. It's not like an ion. It doesn't use the word ion, therefore it's going to be neutral. And we have to first corduroy. Sorry. Hush. There's a dog outside barking. Good boy. Isn't he cute? He's a good boy. Okay. So sulfur dioxide is going to be neutral. We're just telling you there's probably some way we can get the formal charges to equal 0. Because it is neutral. So let's go ahead and start by looking at the sulfur. We'll put it there. It's the least electronegative. It's got to go in the center. And then we're going to add to it 2 oxygens. Well, when oxygen's formal charge is neutral, it's double bound. So therefore, we automatically know that this should probably have double bonds for the oxygen. Now, all we need to do is place the electrons. Well, sulfur plus 2 oxygens gives you a total of 18 valence electrons we need to place. So if we go to count this, we have 2, 4, 6, 8, 10, 12, 14, 16. We need 2 more. Let's put them there. And hey, that works really, really well because valence minus sticks minus dots for sulfur would give you a 0 formal charge. We have 0 formal charges on all 3 of these things, and this is SO2. All right, now we can move on to the actual question. It wants to know about the bond angles, etc. Well, the electron geometry, this has 3 things. 1, 2, 3 things around it again. 1, 2, 3, which tells us the electron geometry wants to get all these electrons as far away from each other as possible. It would be about 120 degrees if these were all atoms. The electron geometry is trigonal planar. Molecular geometry, however, we have taken one of the things and put a lone pair there. So our molecular geometry would be bent because all you really see is this guy, and they'll be bent like this. Now, are they bent a lot or bent a little? The question remains, or the question comes down to how many lone pairs there are. So if there's 2 lone pairs, they're bent a lot. If there's only 1 lone pair, they're bent just a little. So our bond angle has to be less than 120, but not by that much. It's about 116 degrees. So therefore our answer right here is B. Moving on to the next question, which is polar. Cis means same, trans means different. So let's go ahead and draw these out. We have a double bond because they're both enes, ene and ene, and one has a fluorine on one side, or the same side. This would be our cis isomer, and then over here we would have a trans, meaning opposite, like so. So this would be trans. Now if you picture these little fluorines as people pulling ropes, like they're pulling up a rope in a game of tug of war, and you ask which one's gonna win, the one that's going to win is going to be this one right here. It has an overall dipole headed this way. And over here you have one going up and one going down. They're going to cancel each other out. So the one that's polar is definitely going to be the cis. This one is not polar. Now, keep in mind that hydrocarbons are not polar. So for example, if you had something like carbon double bonded to a carbon, and maybe you had a methane group, like this, something to this effect, this would be not polar, because again, hydrocarbons in and of themselves are not polar. All right, let's look at propane combusting now. Propane, we can draw it out, maybe we'll draw it just above it, is going to have 3 carbons because it's prop, each singly bound because it's ane, and then we simply attach the appropriate number of hydrogens. Now when you do this, you find out that it's C3H8. is the compound. So it says it's going to be combusting, which means it's going to react with O2 to form CO2 and H2O. If we go to balance it, and we'll find out that there needs to be 3 carbons on this side. If you remember, we do CHO. So we got 3, we had 1, now we have 3. Over here on the hydrogens, we have 8. So we need to put a 4 over here. So now it went from 2 to 8. And then when we look at the oxygens, over here I have 2. Over here I have 3 times 2, which would be 6, plus 4, which would be 10. Now keep in mind, and so this would be 5 over here. Now keep in mind, sometimes you'll get an odd number over here. You just put the fraction over here and then multiply everything by 2, just as a reminder. All right, so in this case, we didn't need to multiply everything by 2. It worked out very well. Now we can start looking at the bonds. Let's go ahead and start by redrawing these compounds, but actually thinking about what they look like. So again, carbon is 3 carbons. And we're reacting this with 5 O2s, which would look like this. And they're going to form 3 CO2s, which would look like this, and 4 waters. Oops, let's do this again. Let's do them up here. Okay, so let's look at the total number of bonds we have that we're gonna break and that we're gonna form. It looks to me like everything broke. So here we have a carbon-carbon, another carbon-carbon. We broke a total of 2 carbon-carbon bonds. We broke a total of 1, 2, 3, 4, 5, 6, 7, 8 carbon-hydrogen bonds. Then we broke a total of 5 oxygen double bonds. On the product side, we formed, each CO2 has 2 total CO bonds, 2 C double O's. So now we have 3 times 2 C double O's for a total of 6 C double bonded to O's. And then same kind of issue with water. Each one has 2 OHs in it. And we have 4 of those for a total of 8 OH bonds. Now that we've got that figured out, we can kind of plug and chug. So let's go ahead and look at the numbers. We have 2 times 347 kilojoules per mole, plus 8 times 413 kilojoules per mole. Sorry, I won't include units. Plus 5 times 498 kilojoules per mole. Plus, and a good thing to do is remind yourself that these must be negative, because energy is released when bonds form. So now we have 6 times our C double bond O over here, which is 805, so 6 times negative 805, plus 8, and the OH minus is negative 464. When you do this, you get an answer of negative 2054 kilojoules, which would be negative 2.05 E3 kilojoules. So it's a good idea to keep in mind that these are estimated. So really, technically, we're estimating the reaction enthalpy. The actual enthalpy is somewhere around negative 2200. So it comes out really close, and it's a really, really strong, good estimate. All right, let's move on to this last one. What is the hybridization of Br and BRF3? We should note it's neutral again, which is telling you that things are pretty happy. So bromine is probably going to be forming single bonds with fluorine. And fluorine will therefore, so fluorine will therefore make these single bonds and it'll be happy that this would have a 0 formal charge. Valence minus 6 minus dots for all the fluorines will be 0. Now if you calculate the total number of electrons you need, each one has 7 times 4 would be 28 electrons. So when you go to count, you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We still need 4 more electrons, but that's good because right now bromine has a positive 4 formal charge. So we just simply place these 4 electrons like this. Now we can figure out the hybridization. It's got 5 things around it. Again, it's S, P, 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 D, 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 D. We have 5 things. 1, 2, 3, 4, 5. And it's sp3d. This would also, just for fun, be T-shaped. And that's just a good thing to know. All right, hope this helps. Good luck, study hard. Bye.